In this video, I'm going to solve these trigonometric equations for all solutions. Last time we just solved on the interval of 0 to 2 pi. Now we're going to find all solutions using the period of these functions. So let's start off with number 10. Cosine of theta is equal to 1. We're only going to have one place that happens on the first revolution, and that's going to happen when theta equals 0. So theta is equal to 0 plus 2k pi. K is some element of the integers there. So we use a bold Z or a Z with an extra line here to represent the set of all integers. Integers are positive and negative whole numbers. That tells me that I can go whole revolutions, 2 pi. If you want to write this as 2 pi times k, so that makes it easier to see what I'm saying. 2 pi is a full revolution. I can go full revolutions around in the clockwise or the counterclockwise direction and get to the same place here. So since we're adding 0, we're not doing anything. Theta is all the even multiples of pi, like so. Again, k is an element of the integers. That was number 1. Number 2, sine is going to be equal to 1, so that only happens at pi over 2. Again, the period of sine is 2 pi. So that's our answer right there. If we want to put everything over a common denominator of 2, we can do that. Like so. Number 3, sine of theta is 0. Well, that happens at 2 places. So my first set of answers are theta is equal to 0. And my second set of answers is theta is equal to pi. But really together, these are every multiple of pi. If I look here, that it's here, and then there, and then there, and then there. So even and odd multiples of pi is that theta is equal to pi k, where k is an element of the integers. So 14, sorry. We just did 13. No, that was 12. This is going to be 13 now. 13 is the cosine of theta is going to equal to 0. So that's going to be at pi over 2, and then again at 3 pi over 2. But if I look at those two things together, then those are odd multiples of pi over 2. So 2k plus 1 is an odd number. If I start with k equals 0, 0 plus 1 is 1, 1 pi over 2, then k is 1 is going to be 3 pi over 2, and I can keep moving in that direction. If I make k negative 1, then this is negative pi over 2, then negative 3 pi over 2, and so on, and I get all of my answers that way. Let's move on to number 14. Sine of theta is equal to root 3 over 2. So the two places where sine is positive is quadrant 1 and 2. I've got a sine value of √3/2. So that's going to give me a set of answers that start with pi/3. And I've got a set of answers that start with 2pi/3. I'm not going to be able to compress these into a single answer like I did in the previous problems here. I'm just going to have to leave this as two sets of answers like that. If I wanted to write these with a common denominator, it would be something like that. For number 15, tan of theta is equal to -1. So theta is -1 at pi at 3pi/4, and then again at 7pi/4, but that's pi units away. So I'm going to start with my first place, and I'm just going to say k pi because the period of tangent is pi, not 2pi. So k is an element of z. So for number 16, cosine of theta -1 equals 0. So cosine of theta is equal to 1. Cosine is only 1 at 0, and then again at 2pi, and so on. So this is the same problem as problem number 10 up there, that theta is equal to 0 plus 2pi k. So theta is equal to 2pi k. Look at number 17. 2 cosine of theta plus 1 equals 0. So 2 cosine of theta is equal to -1. Cosine of theta is equal to a -1/2. If cosine is negative, I'm in quadrants 2 or 3. So this is a -1/2. I have a reference angle of pi/3. So that's 2pi/3 or 4pi/3. And 2pi times k, 2pi times k. So if I want to make this over common denominator, this is 2pi plus 6pi k/3, and this is going to be 4pi plus 6pi k/3. Number 18, cosine of 2 theta is equal to √2/2. We already talked about how to deal with 2 theta situations a little bit ago, but since we're not on an interval of 0 to 2pi, let's think about how this is going to happen. So 2 theta is going to be equal to this, or 2 theta is going to be equal to this. So cosine here of √2/2, that happens at pi/4. It also happens again at, let's just call it -pi/4. It doesn't matter that I force these things to be positive. It just matters that I pick the first one in the set, and then the period of cosine is going to be 2pi k. So now this group here is going to be pi/8 plus pi k, and this group here is going to be -pi/8 plus pi k, and that will generate all of my answers. I'm going to have two sets of answers here. And they're just going to happen twice as often as I would have expected because of this multiplier of 2 here. So my period is only pi instead of 2 pi. All right. Let's look at number 19. Cosecant of theta over 3 is equal to 2 root 3 over 3. So that means that sine of theta over 3 is equal to root 3 over 2, which is the reciprocal of this. So theta over 3 is equal to pi over 3 plus 2 pi k, or 2 pi over 3 plus 2 pi k. I'm going to multiply by 3. Pi plus 6 pi k. 2 pi plus 6 pi k. So that looks to me like that could be something that would be able to be simplified down, because if I'm taking all of the multiples of, if I'm taking pi and then going around 6k pi, and I'm taking 2 pi and going around 6k pi, then I should be able to say that it's going to be anywhere on this line but every 3 revolutions. But I'm just going to leave it the way that the answer is here. Let me actually look if there's a simplified answer for that one on the answer key. 1 second. Nope, that's the only answer that's given, so we're done. So that's it for this set of problems. Next time we're going to come back and we're going to solve some equations again on the interval of 0 to 2 pi, but we're going to find points of intersection here. So come back and we'll talk about that next time.